Hi you guys. This is notes number 4 from unit 1. We're wrapping up this unit here, and this will show you guys what limits really do and how it connects into the next big idea here. But go ahead and jot down this section here, 1.4, AROC versus IROC. I'll talk about that in a second. And here's our FLT. Go ahead and pause and play whenever you're ready, okay? So here, given a function, you're going to be able to find the average and instantaneous rates of change. So average rate of change, we'll shorten that to AROC, and IROC will be instantaneous rate of change. By the end of this lesson, know what it means and know what it really represents, okay? So here's a little bit of a review, okay? Here's what I'm going to have you guys do. Take a look at this picture here. This is something that you guys learned way back in Algebra 1 or Integrated Math 1. Maybe even in middle school, okay? But here's what I'm going to ask you guys. Here it asks us to find the slope of this line. So I want you guys to remember not just how you find the slope, but what is slope, right? What does it mean to find a slope of a line? What does slope define? Okay, so you got to understand that slope, in terms of a picture, you're really looking at the steepness of a line. Okay, is it shallow or is it really steep, right? But what does it really mean? So we're really finding a rate of change. We're finding how fast something is changing over time. Okay, so I'm going to have you guys pause here in a second, but given this picture, I want you to find the slope, okay, however way you remember it, okay? So however you want to find the slope, go ahead and do it now. Pause it, press play whenever you're ready. Okay, so I'm hoping that you would have done either of two things. So given this picture, some of you remember slope as rise over run. And then this is where you pick two data points. Okay. And then you rise 2, and then you run 1. So that means the slope here is up 2 to the right 1. So our slope here is 2. Our rate of change is 2. Okay. So here's my question to you guys. Can I pick any two data points, right? Can I pick this one and this one here, right? How much would I be rising here? So it looks like we're rising 1, 2, 3, 4, 5, 6 units, okay? But we're running 1, 2, 3 units. Well, what's 6 over 3, right? Notice how we still get the same answer, right? So does it really matter which two data points we pick here? The answer is, for this function, no. You can pick any 2 points you want, as long as you rise and run appropriately, right? Okay. Now, some of you may have found the slope like this. Some of you might have chosen 2 points, -1, -1, and 2, 5, and then you remembered that slope was this equation where it was like y2 minus y1 over x sub 2 minus x sub 1. You could have done that as well. So that would have been just 5 minus -1 all over 2 minus -1. But notice how you still get 6 over 3, which came out to 2. So it doesn't matter if you did it by graphical approach or analytical approach, kind of like how we did it for limits, right? So, okay, so we found the slope, okay? This right here is called an average rate of change. What you guys want to jot down is, whenever you have two data points, you are finding the average rate of change. Okay? Average rate of change. So here's my next task for you guys. So we know that slope is similar to average rate of change. We were able to use rise and run, or some people might have even used the formula, but it doesn't matter, right? Now I give you this picture, and you could jot it down, sketch it real quick. And then here's what I want you to do. I want you to find the slope. What's the slope? Okay, pause and play when you're ready. So some people might say, well, you know what? Well, I'll pick these 2 points. Okay, so that right there, that looks like I'm rising 1 and running 1. So the slope must be 1 over 1, which is 1, right? Okay. But here's the thing. What if I chose instead... What if I chose this point and this point? Do I get the same thing? So it looks like I'm rising 4 and I'm running 2. Well, 4 over 2 is 2. So wait, is the slope 1 or is it 2, right? Now what if I picked 2 different points? What if I picked this point here and this point here? That looks like I'm rising 3 units and I'm running 3 units. Okay, well 3 over 3 is 1. Okay, let's try one more. Now what if I chose this point here and this point here? Well, it's looking like I'm not rising, but I am running 4 units. So I'm rising 0 and running 4, so the slope is 0. So we're getting very different answers here. So what the heck, right? So here's the thing. With linear functions, your average rates of change will always be the same because of the way a linear function works. Okay? When you're getting paid $15 an hour, you will always get $15 for every hour that you work. That is something that works linearly. Okay? But in real life, there are a lot of different patterns that don't work linearly. Let's say you guys were driving to your relative's house, right? You're not traveling at a constant speed. Sometimes you may be at a light and you're waiting there at 0 miles per hour. If you're on the city streets, you may be driving 40 miles per hour, but if you're on the freeway, you might be driving 65 or higher, right? So your rates are constantly changing. Your speed is constantly changing, all right? And this is the whole idea of calculus. How do you calculate rates of change when it's constantly changing? Okay, so it is a new concept, so here's what I want you guys to think about. Now, for those of you that picked these 2 points, you guys actually found the average rate of change of that dotted line right there. For those of you that picked maybe 0 and 2, you guys found the average rate of change between 0 and 2. Okay, now we also demonstrated, well, what if I pick these 2 points? So all of those average rates of change are actually not incorrect. Okay, they're actually accurate. But based on the 2 data points that you picked. Okay, so if we're talking about average rates of change, those are the correct answers. But here's my question to you guys. Now, this isn't the exact representation of you driving a car, but I want you to think about it here. Let's say that this does represent how fast you're going. Is it possible to find how fast you're going at one particular moment? Okay? Can we see the slope at that point. And that's calculus right there. How do we use what we know about limits to find out how fast you're going exactly at one moment? Can I figure out how fast you're going exactly at 12:30 p.m. in your car? Right? So this right here, what we're doing is we're finding the instantaneous rate of change. Pretty much, notice how IROC, there's only one data point, whereas an average rate of change requires 2 data points. Okay? Weird at first, so let me give you guys a scenario here, okay? So if you've ever been to Florida, there are pockets of Florida where there's toll booths central, okay? In order to drive around, you need to hit a toll booth and then another toll booth. So here's a scenario for you guys. You're driving and you reach a toll booth, and what happens is when you go to that toll booth, they give you a receipt, okay? They give you a timestamp of when you got the receipt, your license plate number, and also like a mile marker. So you've reached the 20th mile, okay? And what you do is at every toll booth, there's a person there to give you a receipt. So let's say you're driving at 12 o'clock, okay? You've reached the 20-mile marker, and then you get to your next toll booth, okay? At 12:30, you reach the mile marker 60, okay? So here's what happens when you get to the second toll booth, right? There's a guy right there, and instead of a receipt, he actually gives you a speeding ticket. Okay? So here's my question to you guys. How did that guy know that you were speeding? Okay? Pause. Think about this scenario right here, this toll booth scenario. Think about how that guy knew that you were speeding. And then press play when you're ready, okay? So the reason why that toll booth operator, the reason why he knew that you were speeding is because over the duration of from 12 to 12:30, it's been 30 minutes. Okay? And from mile marker 20 to mile marker 60, you've traveled 40 miles. Okay. So how fast were you going? Right? Well, if you travel 40 miles in 30 minutes, then that means you traveled how fast per hour, right? So 30 minutes is half an hour, and you traveled 40 miles. So that means you were actually going 80 miles per hour. And we all know that the average speed limit for a highway is around 65 or 70, depending on where you're driving, right? So this toll booth guy used the idea of average rate of change and found out by average rate of change you were driving on average 80 miles per hour, so he had the right to give you a ticket. Okay? So what I want you guys to do is I want you to remember this, because we're going to refer back to this even when we're learning new concepts in January or February, okay? This right here is called the toll booth scenario. Okay? It's an example of an average rate of change. This guy needed 2 data points, or 2 receipts in this case, to prove that you were speeding. Okay? That's the toll booth scenario. Okay, so here's your second scenario. All right? And I'll read it out loud for you guys. You don't have to write this part down, just think about the scenario. So at a particular moment, you were driving on the freeway going 75 miles per hour. Okay? Cop turns on his light, he pulls you over, and then he asks you, do you know how fast you were going? And then you said, yes, but officer, you should have seen me in the last 59 minutes. I was only going 50 miles per hour. Okay? So, question for you guys, very obvious answer. What ends up happening, right? So what does the cop do? So he ends up giving you a ticket anyways. So the fact that you said you should have seen me the last 59 minutes, I was only going 50 miles per hour, was that enough for him to let you go? Right? So this right here is, let's give you a scenario. We're going to go back to this picture. When there are two data points, okay, you're creating a line that cuts through a graph twice. That is called a secant line. You might have heard of that word in geometry. You learned it, but you didn't really know what was the purpose of it, right? Everything wraps up nicely in calculus. So when you're finding the slope of a secant line, you're really finding the average rate of change, which is the toll booth scenario. Okay? Make sure that you guys jot this one down. So that toll booth operator needed 2 whole receipts or 2 data points to prove that you were speeding. Now that second scenario, the cop scenario, how does a cop or police officer catch you speeding? Right? What do they use to catch you speeding? So they use that radar gun. You might have seen it in TV shows, or if you know a family member that is a police officer, they use a radar gun to catch you speeding. So what happens is, if you know how a radar gun works, okay, what happens here is I'll draw you some pictures. It's not the best illustration. So imagine that there's a radar gun. This is your radar gun. I'm bad at drawing. What it does is he will capture your car, okay? What that does, at a very fast speed, the radar sends out a laser or an invisible beam. What he does is he shoots that radar right at your license plate, and as soon as that laser hits that license plate, it'll bounce right back to the radar gun at a very instantaneous speed, very fast, okay? So what the radar does is it collects 2 data points at a very fast moment, almost to the nanosecond. So if it was like 1.00 seconds, if it starts there, the radar will come back at 1.00001 second. Probably even faster than that. Okay? Almost to the point where it's almost instantaneous. So when the cop uses his radar gun, really what's happening here, and I'll show you a visual, he's finding out exactly how fast you're going at one particular moment. And that right there, and make sure you illustrate this, is an example of a tangent line. Back in geometry, when there was a line that intersects a curve exactly once, you call it a tangent line. And if we study the slope of a tangent line, that is an example of an instantaneous rate of change. We'll call that the cop scenario. So when the cop uses that radar gun, he's really finding just one exact moment to see how fast you are going. Now I want you guys to think about that, because we've been so stuck with using 2 data points all the way back from Algebra 1, right? How do you find the slope of a line when you only have 1 data point? How do you rise and run if there's only 1 data point, right? And that's where the concept of limits come in. It almost seems a little bit impossible to find the slope at one moment, but using what we know about limits, I'm going to show you how we can kind of graduate from linear functions and be able to find out how fast you're going at any particular moment. Okay? So make sure before you move on here You understand that the toll booth scenario is an example of an average rate of change, otherwise known as AROC. That's the slope of a secant line. And the cop scenario is an example of an instantaneous rate of change, or IROC, okay, which is the slope of a tangent line. All right. Make sure that you guys understand that all of these statements are synonymous to each other, okay? They mean the same thing. Okay, so to illustrate this, I'm going to give you guys a heads up. We'll be using our calculator here to speed up the process because we don't want to get caught up in all of the computations here, okay? All I want you to do for this example, we'll call it example 1. All you have to do is jot down this table. Press pause and then play whenever you're ready, okay? Okay, so here we're talking about a cardiac monitor is being used to measure the heart rate, okay? So they're capturing the amount of heartbeats in a patient after surgery, okay? So, for instance, the 36th minute, the patient recorded 2,500 heartbeats, okay? On the 40th minute, 2,800 heartbeats. 44th minute, about 3,000 heartbeats, and so on, right? So, what we're going to do is, first we want to find out, well, what's the average rate of change, right? How fast was your heart beating from one point to another, okay? So here it says the monitor estimates this value by calculating the slope of a secant line. Use the data to estimate the patient's heart rate after 42 minutes using the secant line between the points with the given values of t. Okay, so we're going to break this up into pieces here, okay? So what we want to do is we want to gather information from the 36th minute and the 42nd minute. To find the slope between two moments, we're finding the slope of a secant line because there's two data points. So we're finding the slope of a secant line, also known as average rate of change. Okay? So at the 36th minute, we have 2,530 heartbeats. Okay? At the 42nd minute, we have 2,948 heartbeats. Well, how do you find the average rate of change or the slope of a secant line given these 2 points? So remember, going back all the way to the beginning of this lesson, when you're given 2 points, you can find the slope of that line. So I'm going to use the analytical approach here. So to find the slope, that's just y2 minus y1 all over x sub 2 minus x sub 1. Okay, so don't do this in your head. Go ahead and type it out, but make sure, because if you don't type it correctly, when you turn on your calculator, make sure that when you type it, you group the numerators and the denominators. I'll give you a second to do that. Okay, and then you should get, oh gosh, I should have computed this myself. Let me do this here. So 2948 minus 2530 divided by the 6. So you should have gotten about 69.667. Okay, if you didn't get that, you probably either mistyped a number or you didn't include the parentheses, okay? Now I want you guys to think about this. 2948 and 2530 represented what, right? It represented heartbeats. So we're going to be left with heartbeats, which I'll just put HB. Now 42 and 36 were representations of minutes. So this is going to be heartbeats per minute. Okay? So from the 36th minute to the 42nd minute, this is how fast your heart was beating. Okay? Roughly around 70 heartbeats per minute. Okay? we're going to do the same thing. So here, let's do it one more time. Part B, we're focusing on the 38th minute and the 42nd minute. Okay, the 38th minute we have 2,661 heartbeats, and the 42nd minute we still have 2,948. All right, go ahead and pause and then play when you're ready. So you should have 2,948 minus 2,661 all over 42 minus 38. Let me go ahead and compute that real quick. 2,948 minus 2,661. Okay, so you should have gotten 71.75 heartbeats per minute. So notice how when you're comparing the slope of a secant line from the 38th minute to the 42nd minute, your heartbeats are a little bit different. Your heart is beating at 71 beats per minute. Okay? So the answers are a little bit different. I want you guys to go ahead and do parts C and D and then play when you're ready, okay? So here you should have 2,948 minus 2,806 all over 42 minus 40, and that should give you 71 exactly heartbeats per minute. Okay, if you didn't get that, remember, use parentheses. All right, and over here, let's see, we would have 3,080 minus 2,948 all over 44 minus 42. That'll give you right here 3,080 minus 2,948 divided by. That should give you 66 heartbeats per minute. Now, if you didn't get that, make sure you text me, okay? So what does this all mean? These are all examples of average rates of change, okay? So here's the question. We're trying to find out, well, can we figure out how fast our heart was beating exactly at the 42-minute mark? Okay? Here are all the examples of average rates of change, right? Okay, so here's what I want you guys to think about. Let's go back to that graph, right? Let me go back real quick. Here we go. Okay, so think about it here. Similar to our problem, this is not the exact graph, okay, because we don't know what it looks like. I am going to draw many secant lines. Here's an orange one. Here's a red one. Here's a green one. Here's the purple one. Okay, all of these are secant lines because they're intersecting the curve twice. There's two data points, right? Now, imagine, I mean, this isn't the exact graph, but imagine that you recorded all of these rates of heartbeats per minute, right? If I asked you, well, how fast is my heart beating exactly at this pink moment, just this one moment, okay? If you take a look at this, which secant line would be the best estimate to represent how fast your heart is beating at that one pink moment? Okay, I'll say that one more time. Which, out of the four secant lines that you see here, which one would be the closest estimate to how fast your heart is beating exactly at this moment? Okay, play when you're ready. I'm hoping that everyone would say the purple line. Now, why is the purple line the better estimate for how fast your heart is beating at that one moment, right? The reason is because your two data points are super close to that pink data point. Okay, all these other orange, red, and green data points are good, but they're not as good as the purple one because the purple 2 data points are closer, and if they're closer, it'll be a more accurate representation of how fast your heart is beating. Okay, so the rule is the closer you are, the better the estimate. Make sure you guys write that down. The closer you are, the better the estimate. Okay, so let's take a look at this problem again. We want to find out how fast your heart was beating exactly at the 42-minute mark. Okay, so let me draw a picture for you guys. Let's say that this is 36, 38, 40, 42, and 44. You don't have to draw this one out here, okay? So I am trying to figure out how fast my heart is beating exactly at the 42-minute mark, okay? So would I use 2 data points that had 36 and 42? Okay, so that's not necessarily the slope, but I used, this is part A here. I used the 36-minute and the 42nd minute mark. In part B, I used 38 minutes and 42 minutes. Okay, in part C, I chose 40 minutes and 42 minutes. And at part D, I chose 42 minutes and 44 minutes. Which would be the best estimate? Right? So part A, B, C, or D. Pause and play when you're ready. Okay, so I'm hoping your answer would have either been C or D. Now, part A and B would not be a good answer because in part A, that's a 6-minute spread. That's a 6-minute difference, right? Whereas part B is a 4-minute difference. So we're getting a lot closer. But notice how in part C, you're only 2 minutes apart. So your 2 data points are a lot closer to each other. But so is part D. So this is like a rare case where it's kind of like a tie. Part C and D would be very good estimates to exactly how fast your heart is beating at the 42nd minute mark. Okay? So, here's what I want you to think about. Let me clear this page here. If I want to know exactly how fast my heart is beating, or the rate at the 42nd minute mark, that is an example of an instantaneous rate of change. Okay? And the best estimate I could use is either part C or part D, because they're equally distant, right? So normally if you have a list of average rates of change, you would pick the one that's closest together, but in this case there's a tie. So what you would do is you would just find the average of the two. So here there's 71 heartbeats per minute and 76. So you would just find the average of the two, whatever that comes out to. 137 divided by 2. Oh gosh, what is that? Let me type that in. So the best estimate, this is the best that we can do, is say that at the 42nd minute mark, your heart was probably beating at 68.5 heartbeats per minute. Okay? Now, we used estimates of average rates of change to make a prediction on how fast your heart is beating at one particular moment. We used the toll booth scenario to give us an estimate of how fast our heartbeat is beating at one particular moment. Okay? So, is it even possible to find out how fast anything is going at one particular moment? right? So I want you guys to think about it here. In theory, could we make our estimates even better? Right? We can make our estimates better if we were able to find 2 points that were even closer. For instance, the 43rd minute or the 41st minute, right? If we compared 42nd to 43, we would get an even more accurate estimate, right? But because we only have a table, the closest that we can get is 40 and 42 or 42 and 44. Now, theoretically, could we make our estimates even better, right? Could I pick something even better than 41 and 42? Okay, so if you guys have the power, could you make that estimate even better? So the thing is, you can. Well, what if I chose the 41.5 minute mark and the 42nd minute? That's an even smaller window. What if I picked 41.7 minutes and the 42nd minute? My average rates of change is a lot closer to that 42nd minute. Okay, so in theory, how far can you go? Okay, so hopefully you guys are saying closer and closer and closer. And I'm going to ask you, well, how close? Hopefully you guys are saying this. How close can we actually go? We want to get as arbitrarily close as possible. Do you guys remember where we got this phrase from? Right? That's the whole concept of limits. Okay? Based on this problem, we couldn't get as arbitrarily close as possible, so we picked the two closest points. They were equally distant, so we had to average them out. Okay? Okay, so here we go. Last problem. Okay, so here's the last example. This one's a little bit different because you're not given a table. You're actually given a, if you can see here, you're given a function. So it's a little bit different in that you could actually do a little bit more with this, okay? So for the sake of this problem, this is actually my take 2 here. I am going to speed up the calculations for you guys so that you don't get so caught up with the calculations, because that's not the big idea of this problem here, okay? So here's what I want you to understand. We have this rock, so it's not a cardiac monitor. What you're doing is you're taking this rock and then you're throwing it, and it creates kind of like a projectile motion, like a parabola, right? So that function is what that parabola is going to look like, okay? So they're going to ask you to find average velocities at certain time intervals. So right here, I want to know how fast the ball is going from time t equals 1 to time t equals 2. Now I'll demonstrate the first one, and then we'll kind of speed it up here, okay? So what you guys want to do is you want to know what the two data points are. We're finding the average rate of change. So what you would normally do here is you would type in your function and then input some values, but I'm going to cheat a little bit here. When you plug 1 into that function, if you plug 1 in here and you compute it, you're going to get a value, but I made a table right here. So if you take a look at the bottom left, at 1, it comes out to 8.14. And at 2, it comes out to 12.56. Just trust me on these values, only because that's not the big point of this problem here, okay? So if you found the average rate of change, or the slope, if you did this there, and I kind of created a formula for it, if you look right here, it comes out to 4.42. Just trust me on it. So 4.42 meters per second. That's how fast the ball was going. Now, we're going to do the same thing 4 more different times, but instead in part B, I'm going to go from t equals 1 to t equals 1.5. Okay, so that's t equals 1 to t equals 1.5. And then I'm going to do the same thing, but we're just going to speed it up, okay? So based on my Desmos, where I will generate all the values, okay? Just to get you guys to understand the bigger picture. If I compare 1 to 1.5, I will get a slope of 5.53. Again, don't worry about confirming these answers. 1.53. Is it 1.53? Sorry, 5.35. Where am I getting that from? 5.35. Okay. Maybe close your eyes so you don't get dizzy. 1.1, the slope came out to 6.094. 1.01 is 6.261. And the last set will be 6.278. Okay? What does this all mean, right? So remember, we're trying to figure out, if you read in part B, we're trying to find out how fast this ball is going exactly at this moment. This is kind of like that cop scenario. How am I going to figure out how fast I'm going at one moment, right? So we use what we know about average velocities or average rates of change here. So I want to demo for you guys right here what we're actually doing. So let me go back and change this to 2. Okay. If you guys take a look, let me zoom out a little bit. That purple graph right there is you tossing that ball. Okay? Now, there are 2 data points. Right here is at time 1, and that orange dot you see right here is at time 2. I drew a line there, I connected it, creating a secant line. And from there, I can find the slope of it, or the average rate of change. So right here, I created a formula to calculate the slope quickly. You guys don't have to know how to do that. But it came out to 4.42. Now, then I went from 1 to 2 to 1 to 1.5. So pretty much that point got closer. Okay? Now it goes back to that cardiac monitor problem. How do you decide which average rate of change is going to be the best estimate? So remember what we wrote down. The closer the 2 points, the better the estimate. So how good can we get this, right? So hopefully you understand that. Let me just let that run. The closer and closer that orange point moves closer to t equals 1, notice how that slope is constantly changing, but the slope is getting more accurate. Let me speed this up here, okay? If you move those 2 points as close as possible to each other, arbitrarily close but not exact, you will get an even better and better and better and better estimate. Okay, so actually if you move those 2 points to the point where they're almost on top of each other, if you take a look, you're actually creating what looks like a tangent line. And that's the concept of it, okay? You're making 2 points get arbitrarily close to each other, and then you're studying the behavior of the slopes. So, to answer this question, out of parts 1, 2, 3, 4, and 5, the one that will best estimate the instantaneous velocity at t equals 1 would have to be part 5, because these are the 2 points that are closest. Okay? And the closer the 2 data points, the better the estimate. And that's the big takeaway, you guys. You want to get as close as possible for your average rates of change, and that'll be the best estimate possible here. Now here, because we were given a function, we could actually get as arbitrarily close as we wanted to. How would you guys make an even better answer, right? What 2 data points would you pick? Play when you're ready, okay? You could even go from 1 to 1.000001 if you wanted to, get a better estimate, okay? So roughly at t equals 1, your ball was probably going at 6.278 meters per second, okay? Now, just to reiterate, because a lot of people have this question on the homework, in this cardiac monitor problem, we were not given the function, so we were not able to get as arbitrarily close as possible. Actually, we were only able to get as close as from 40 to 42 and from 42 to 44. They were equally distant, so we actually had to average those 2 out, okay? So when you're given an equation, it changes things up a little bit, but when you're only given a table, you only use what you know about that table, okay? So all in all, make sure that you guys understand the differences between average rates of change and instantaneous rates of change. I go back to this before I conclude. The toll booth example is an example of average rates of change, otherwise known as the slope of a secant line. The cop scenario, where he uses the radar gun, is an example of an instantaneous rate of change, also known as IROC, is when you're finding the slope of a tangent line. Okay, that's it. Think about that. Try the homework out and let me know how it goes.